Hi everybody, today we are going to talk about some of the applications of determinants and matrices. So one of those applications is what's called Kramers Rule. It's yet another way to solve a system of equations. So if you have a system with n variables and n equations, we can find each variable by finding the determinant of what we'll call a sub 1, which I'll talk about in 1 minute, divided by the determinant of matrix A, which I do want to point out is the coefficient matrix. So one thing you might notice is that all of your equations have this determinant of matrix A in your denominator. So whichever variable you're solving for, that will always be there. So that should be the first thing that you find, because if this determinant is 0, and we can't divide by 0, and that's when you have no solution. Now, if you check this and it is not 0, there's going to be a solution. So then you have to go through and find the determinant of these matrices. So the way that you set these up is essentially whatever column this is, you replace that column with your column of constants. So here we have an example. Here they're finding the determinant of matrix A sub 3. So you can see that this is what our coefficient matrix is, and since it's for A sub 3, they replaced the third column with the constant column. So if you are solving for your first variable, you replace the first column with these b's. If it's the second variable, you replace the second column, and so on and so forth. And then you just divide those two determinants, and that will be your answer. So this is definitely one of those things where it's easier to show rather than to tell. Let's try an example together. So here we just have a system of two variables. So we are going to set up, well, first we're going to set up our coefficient matrix. So our coefficient matrix is going to be 4, -2, 3, -5, and we're going to find the determinant of that. So here we have -20 minus -6, so it's going to equal -14, which means that we do have a solution. So we're going to continue on with this problem. So the next two things we're going to find the determinant of A sub x. So remember, we find that by replacing our x column, which is these numbers, with our constants. And then we find the determinant of that new matrix. So our y column is going to stay the same. And then you can find that determinant, and you should get -28. And now we're going to find the determinant of A sub y. So now we're going to replace our y column with our constants. So the determinant of that should be, so it's 44 minus 30, so it is 14. So now we know the three things we need to find are x and y. So we know that x is just the determinant of A sub x over the determinant of A. So it's -28 over -14, which is just 2. And then y is going to be the determinant of A sub y over the determinant of A. So 14 over -14, which is -1. So our solution is 2, -1. All right, go ahead and pause the video and give this problem a try. Okay. So here, first I checked the coefficient matrix, and it was -11, so there's the solution. So then to find x, we replace our x values with our constants, and to find that y, we replace our y column with our constants and find those determinants, and you should end up with +3 and -2. All right, now we're going to try it with a 3 by 3, but the setup is going to be the same. So the first thing that we're going to check is that our coefficient matrix is not, the determinant of it is not equal to 0. So we have -1, 2, -3, 2, 0, 1, 3, -4, 4. So you can simplify this in any way that you want, but the determinant of this matrix is going to be 10. So if you need a review of how to find the determinant of a 3 by 3, make sure you go back and watch the last video of finding the determinants of larger square matrices. But here we're just going to go through a little bit quicker. So now I need to find the determinant of a sub x. So I'm going to replace my x column with my matrices, or with my constants. Everything else stays the same. And the determinant of that matrix should be 8. Then for a sub y, I'm going to replace my second column with my constants. And the determinant of this matrix should be negative 15. And then last, we're going to replace our z column with our constants. And we should get negative 16. Just a side note, remember you can use the diagonal method or the cofactor method for a problem like this where I see a row or column with 2 zeros, or even like this one. I would probably use the cofactor method. I think it's a little bit faster. So now we have all of the values we need. So now we just have to finish plugging them into our formula. So for x, it's going to be 8 over 10. So it's 4/5. For y, it's going to be negative 15 over 10, so negative 3/2. And for z, it's going to be negative 16 over 10, so negative 8/5. Then we just write it as an ordered triple, and we're done. So you can probably guess that since we have fraction answers, if you tried to solve this using Gaussian elimination, for example, it's going to get a little bit messy. So that's a nice thing about Kramers Rule, that while it might take a little bit of time to do the determinant of your 3 by 3s, it's always going to give you a pretty straightforward answer, even if your final answer ends up being a fraction. So it's definitely a good method to know. All right, go ahead and pause the video and give this one a try. So now you're going to have to do the determinant, so it's a good time to practice that skill. Okay, so the determinant of your coefficient matrix should have been 55. And then, so check the setup. Here I actually went and solved out all of these determinants. And I used the diagonal method for all of them, but the determinant of matrix A sub x should have been 110. The determinant of matrix A sub y should be negative 165. And the determinant of matrix A sub z should be 55. So this is a really good indicator of whether or not you need to go back and practice finding the determinants of those 3 by 3. But when you plug them into your formula, you should end up with 2, negative 3, 1. Okay, so we're moving on to a new application of determinants and matrices, and this is finding the area of a triangle. So this really is for when you have a triangle on a coordinate plane and where you know the 3 vertices, or the 3 coordinates of your vertices. So essentially what you're going to do is you're going to set up a matrix that looks like this. Notice your 3 coordinates are listed here, and your third column is all ones. Now it doesn't matter which coordinate you list first, second, or third, as long as the x and y's are next to each other appropriately. So you find the determinant of that matrix, and then you multiply it by 1/2, and then this plus or minus is here to give you flexibility in making sure that your answer is positive. It does not give us 2 answers. It's there essentially to act as an absolute value to make your answer positive, because once again, we're finding the area. So let's give this one a try. So our area here is going to be plus or minus 1/2 times the determinant of, so now you list out your 3 coordinates, and our third column is going to be all ones. So you can use whichever method you want to find this determinant. But the determinant of this matrix should be negative 3. So of course we're going to want to take advantage of this plus or minus to turn it positive. So our answer for the area should always be positive, and it will be 3/2. And then we'll just say units squared. So once again, I didn't go out and solve or show the work for finding that determinant. So if you need that extra practice, go back and watch the previous video. All right, go ahead and pause the video and see if you can find the area of this triangle. Okay, so here I set up my matrix, and I actually found the determinant of this matrix using the cofactor method because of this column. So remember, for using this column, all these zeros will help us out a lot. So we do the element and then times possibly -1, but this is row 1, column 3, so it's an even sum. So it stays, we don't need to multiply it. And then we find the determinant of what's left over when I take away those two columns and rows. And so the determinant of this should be 18. And then you just go back and multiply it by 1/2. It's already positive, so we're happy. So it's 9 units squared. But if you don't want to use that cofactor method to find the determinant, you can always use that diagonal method. Okay, yet another application. Here you might notice that the setup looks very similar to the last problem, but here we're testing for collinear points. So essentially, if you find this determinant and that determinant is equal to 0, the points are collinear. If it's equal to anything else, the points are not collinear. So here we're actually testing to see what the determinant is. And once again, if it's 0, they're collinear. If it's not, they're not collinear. Let's give this problem a try. We're trying to see if these three coordinates are collinear. So let's set up our matrix, and we're going to find that determinant. So it should be -2, -2, 1, 1, 1, 1, 7, 5, 1. And whichever method you choose for finding this determinant is fine. If you find this determinant, it should be -6. So since it's not equal to 0, the points are not collinear. And it's as easy as that. All right, go ahead and pause the video and see if these three coordinates are collinear. All right, so here I set up my matrix and I use the diagonal method to find this determinant. Remember, you multiply across and you take those sums, and then you multiply across this way, take those sums, and you subtract the 2. So here you find that our determinant is 0, which means that those 3 points are collinear. All right, another application of matrices and determinants is that you can actually create an equation for the line between 2 points. So notice here, it looks very similar to the last two setups, except here we're only given 2 coordinates. So here's the 2 coordinates, and here we actually see x and y. So those are supposed to be x and y. Those are going to be the variables of our linear equation. So it's going to feel kind of weird to find a determinant with variables, but you follow the same exact process. And once again, we are creating a linear equation, so there should be an x and y somewhere in there. So that x and y always needs to be that first row. And then these two, it doesn't matter which order you place those in. And notice that we find that determinant and we set it equal to 0 because it is an equation. All right, so let's give this problem a try. They want to find the line that passes through 2, 4, and -1, 3. So remember, we're going to start by making our x, y, 1 row. So this is going to be the variables that stay in our equation. And then we can have 2, 4, 1, and -1, 3, 1. So we're going to find the determinant of that. I'm going to use the diagonal method. And then we're going to set that determinant equal to 0. Okay, so from here, I'm going to multiply across the diagonals. So I know it seems a little bit weird to do with variables, but it works in the same way. X times 4 times 1 is 4x. Y times 1 times -1 is -y. 1 times 2 times 3 is 6. And then we subtract the other diagonals. Here we get negative 4, here we get 3x, and here we get 2y. And now we just need to combine like terms, essentially. So here we have 4x minus 3x, so we get x. And here we have negative y minus 2y, so minus 3y. And then we have 6 minus negative 4, so positive 10 equals 0. And this is our linear equation. From here, you can put it in whatever form you want, but we have x, we have y, and we have our constant, so we are good to go. All right, go ahead and pause the video and give this problem a try. Okay, so same general setup. I use diagonal method again to find that determinant. Here, I took this and I just simplified it. You don't absolutely have to do this. Technically, this is a valid linear equation as well, but you should get negative 6x plus 6y minus 12 equals 0, which can be simplified to x minus y plus 2 equals 0. From there, put in standard form, slope-intercept, whatever you want. Okay, another application of matrices is you can actually do transformations with them. So here, there's these specific transformation matrices, which you're going to multiply to each individual coordinate, and we write our coordinates as a 2-by-1 matrix. So we have different ones for reflection over the y-axis, over the x-axis, and for both horizontal and vertical stretches. And here it's just matrix multiplication. But you'll see it's the same general idea of when we transform coordinates, just using the rules that we've already talked about. So here we have a square with the following vertices, and we want to reflect it over the y-axis. So our reflection in the y-axis matrix looks like this, negative 1, 0, 0, 1. So I'm going to take that and I'm going to multiply it to each of my coordinates written as a 2-by-1. So we do have to do this 4 times. So then this coordinate is 2, 0. So we have a first row is for x's, the second row is for y's. Then we have 1 for 0, 2. And last but not least, we have 1 for 2, 2. So remember, with matrix multiplication, we multiply across the rows and down the column. So for example, here we'd have negative 1 times 0 plus 0 times 0. So that gives us 0. And then here we have 0 times 0 plus 1 times 0, which is also 0. So if you go through and do the matrix multiplication for each one, here we have negative 1 times 2 plus 0 times 0. So negative 2 and then 0. Here, if you do it, you actually end up with 0, 2, the same exact matrix. And here we have negative 2 times 2 plus 0 times 2, so negative 2. And then we have 0 times 2 plus 1 times 2, which is 2. So if you look at the coordinates we get when we're done, you'll notice that using matrices, we end up with the same result as if we just followed our basic transformation rules. So we know that the rule to reflect over the y-axis is to multiply all of your x values by negative 1. The y value should stay the same. So you can see that negative 2 or 2, 0 became negative 2, 0. These stayed the same because the x values were 0, and 2, 2 became negative 2, 2. So notice that our y values were all unaffected, just as they should be. Okay, go ahead and pause the video and give this example a try. Okay, so here the transformation matrix we use would be 1, 0, 0, 2 because it is a vertical stretch by a factor of 2. And then we have the same for coordinates. We do a little bit of matrix multiplication, and notice that all of our y values were multiplied by 2, which would follow the same rules that we've talked about previously. All right, the last application we're going to talk about today is that you can actually find the area of a parallelogram using matrices. Now, for all the ones that we're going to do, one of the vertices is going to be at the origin. So if we have these 4 coordinates, one of them at the origin, we can set up a matrix A just by doing A, B, C, D. So one of your one of your coordinates to the right and one of your coordinates up. This is kind of the coordinate that's diagonally out, so we don't need to use that in our matrix. So here you just have to be careful because the formula is actually the absolute value of the determinant. So notice they wrote it like this because, as we know, that one of the ways to notate determinant, it actually looks like the absolute value. So essentially you're just taking the determinant of this matrix and then making it positive because it is area. But it's super, super easy to do. So let's look at this example. So you can see that this is going to be that AB, this is going to be CD, or it could be switched. But this is the one that's diagonal. Notice that it's the sum of your two x values and your two y values, so we're not going to use that coordinate. So we're just going to take the determinant of this matrix, 1, 3, 2, 0. And it really doesn't matter which one we put on top or the bottom. So if I do this, we get 0 minus 6, so it's negative 6, and then we're going to take the absolute value of that, so it will equal 6 units squared. So be careful because this is determinant and this is absolute value. So remember, it's the absolute value of the determinant. So just be very, very careful with that. But once you know how to do it, it's super, super quick and easy. All right, here is the last problem. See if you can find the area of this parallelogram. All right, here we have the setup, found the determinant. It's already positive, but the absolute value of it will still be positive. So it's 10 units squared. All right, that is all for today. Thank you for watching.